Chapter 1. It's about the fundamentals of chemistry. It talks to you first about water and then uses that as a vehicle to illustrate how matter is organized and the elements and about thinking as a scientist. So let's get started. Well, the chapter talks about water and how water is very important for our daily lives. In fact, it's the number one chemical that is responsible for life as we know it. In California, you guys know that we are in a drought and water is hard to come by. And California is actually interconnected by some water irrigation that serves over 30 million people, and it has about 5,600,000 acres or 2,300,000 hectares. In fact, this is the world's largest, most productive, and most controversial water system. And the government is in charge of distributing it fairly. You guys know that when there is it's a dry winter, down here in Southern California, we have strict water rationing, and that's because most of our water comes from Northern California. I want to focus in at LA, and the reason why I want to focus in LA is because LA is actually a desert. In fact, the whole Southern California region is a desert. The reason why we have huge cities in Southern California is because there is the Owens Valley, as you can see from that map. In fact, back in the 1920s, 1930s, Mulholland, he was an engineer, outright stole water from the Owens Valley, and the Owens Valley is near Bishop. You can see it's south of Bishop, and I'm going to show you a movie of how that occurred. I'm just going to show you a snippet. If you want to see the full series, it's a 9-part series, and the movie, if you Google Desert Cadillac Mulholland Stream, you'll find it in YouTube.
I have no apologies. I was a crusader for the development of water. I was the Messiah. I was the evangelist that went out and argued persuasively to develop our rivers and water supplies for the benefit of people.
In the American desert, we have built a great new civilization in less than a century, where none could possibly be in the natural order of things. We have made the land wet where it was dry, and dry where it was wet. We have lifted great rivers out of their ancient beds and moved them over half a continent. Our great cities stand in a desert that is drier than the plains of North Africa. It would all be impossible without the breathtaking manipulation of water. We fought over water, thrived on water, and finally, we engineered the desert out of existence.
Next to God, there's water.
Everybody is conscious of water. If you head for the river with an empty bucket, you're liable to get shot. So.
Can you imagine today, an American city, acquiring an entire river?
The idea of subduing nature has captivated the whole country. Congress cannot appropriate enough money fast enough to build more dams.
We built the dams for all the right reasons when they were desperately needed, with little thought to the consequences. developing world watched and envied our success.
The engineering marvel that is Cooley Dam, inspected by Emperor Haile Selassie of Ethiopia.
Supplying water to a population growing that fast is extremely difficult.
It was a little bit like the Sorcerer's Apprentice. You've got to have more water, more water, more water.
They're going to dam this canyon.
There was no end to these people who had plans to dam San Francisco Bay, pipelines beyond your wildest dreams. When this wasn't about carrying oil, this was about carrying water.
We have forgotten that the natural West is barren and fatally dry, and that our new bountiful West is a fragile construction. Here and there are reminders of what happens when the water is turned off, or when the waterworks fail.
Somehow, the water stopped flowing. You'd have a desert again overnight.
The dam's gone.
The whole thing has gone now?
The whole thing is gone. It rolled over about 5 minutes ago.
Okay.
If you can get us any help on radio or whatnot, get the people south of there out.
All right. Where do you want the people evacuated?
Well, we would like to get them off the river in low-lying spots.
Well, it's 6:22 and 710 Talk KMPC. I'm Dominic with Airwatch Traffic, and I got to tell you, the Jackknife Big Rig in Pasadena has the 210 eastbound in trouble right at Rosemead, where the right 3 lanes are out of commission. The Jackknife Big Rig there, and about a quarter-mile slow. On the westbound side, almost across the fence from it, right at Sierra Madre. Right lane is blocked with a car fire, so get ready. It's slow from the 605. And how are things in Orange County? Hey, Scott Forrest, good morning.
18, el Ronald Reagan Freeway al oeste, acercándose a la calle Reseda Boulevard, Monte Vista, accidente de 3 autos.
할리우드 프리웨이로 바뀌는 101번 사우스 방향입니다. 할리우드에서부터 시작해서 다운타운의 다른
Bell Street. It's a car that spun out and hit the center divider, and 2 left lanes are protected by CHP vehicles. Use alternate routes such as Laurel Canyon or even Mulholland today.
I think my grandfather, his vision was a city like Dublin, which was the city of his childhood. And it was a vision, I think, of a 19th century city, where people ambled on streets and knew one another and enjoyed the theater and the opera and the university. A civilized 19th century city.
No other Buick dealership in California has been best in its class for 7 years. That's because no other Buick dealership has sold more than 10,000 Buicks in the last 10 years. The list goes on and on. Right now, we do have lots of traffic to talk about, too. First of all, the KABC traffic alert continues.
The thing that you have to remember about Los Angeles is it never really had a reason to be there. It had no minerals, no metals, no forests. In other words, everything that any major American city used to develop itself, LA lacked. And above all, it lacked water.
Since the beginning of time, this was a place of earthquakes and perpetual drought. First claimed by the Spaniards, and then conquered by the Americans. Virtually everyone here had come from somewhere else. In 1878, William Mulholland arrived from the Green Hills of Ireland. He had stowed away on a sailing ship, worked as a lumberjack, failed as a gold miner, and had walked across Panama to save $25 in train fare. He was fond of one-armed chin-ups and grand opera. Mulholland found work as a ditch digger on the growing town's dilapidated water system.
LA was desperate to become a modern city. It had been a backwater for so many decades. But its water system, on the other hand, was pretty much the same old jerry-built thing. A bunch of old water wheels, a falling-apart system.
He worked hard, read Shakespeare and hydraulic engineering late into the night, taught himself to keep the entire LA water system in his head and climbed through the ranks. In 1886, when his boss suddenly dropped dead, William Mulholland found himself superintendent of the LA water system. The little desert pueblo had grown to 100,000 people, thanks to the Chamber of Commerce and a new railroad. And by 1903, LA had sucked dry the tiny Los Angeles River, its only source of water.
My mother would tell me these stories of growing up without water. One bath a week on Saturday night in a big zinc tub that was dragged into the kitchen and water heated. And Papa got the first bath, Mama got the second, and the kids, and Mother told me, you know, and they were not what you'd call white trash, but she told me she never had a bath in pure, clean water. Now, I was raised with a real sense that water was a precious item and not to be squandered.
Superintendent Mulholland tried to make Los Angeles live within its means, but growth sabotaged everything he did. By 1903, the chief knew that LA would have to stop growing, or he would have to find a new source of water. His friend, Mayor Fred Eaton, told him of a great valley 200 miles to the north.
And that pretty much is the end of part one. Mulholland goes up to the Owens Valley and he cons those people to channeling the water from up there down to LA. Anyway, Google Cadillac Dream and watch the series and you'll be amazed just how LA got started. Anyway, let's continue on with this portion of the course. It's about how matter is classified and that how chemistry is related to everything that we see. The classification of matter is how we organize it. We organize it in terms of its elements. If you put elements together, we have compounds, and if you put compounds together, we have mixture. We'll see more of this shortly. The states of matter, however, are not the classification. The states is how we observe matter, and the states of matters are a solid. It has a fixed shape and fixed volume, like solid ice or your pencil or your keyboard. Liquid is, it takes the shape of its container, but it has a fixed volume, like the water beverage that you're drinking. And gas, it takes the shape of its container and it takes the volume of its container. So these are the three phases of matter. I told you there's actually four, and the fourth phase is plasma. Plasma is actually matter in the gas phase with its electrons stripped. The plasma state is what exists on the sun. Now, the way we describe matter is through its physical and chemical properties. Physical properties is our observation of matter. When we convert liquid water to gas, that's just a physical change because the water molecules really has not disorganized. The bonds weren't broken, and if you take the gas and recondense it, you can get liquid water again. And if you freeze it and melt it, you can get water again. It has the same type of chemical properties, or it goes back to its original form. On the other hand, a chemical property is when you take matter and you break it up into its component, or you react it so that bonds are broken and new bonds are formed. So let's take a look at the phases of matter. You have this gas, the liquid, and the solid. And here you can see that gas are separated by a large distance and they take on the volume of the container. The liquids are much more intimate with each other. The molecules actually tumble amongst each other, and then it also takes the shape of its container. But the solid, however, doesn't take the shape of its container, and it also has a fixed volume. You can go from one state to the other by either applying heat or removing heat. So you guys probably have seen these phases in your life. For example, when it snows, that's a solid form of matter. When that Iceman melts, then that's a liquid form of matter. And then during the day, that liquid will actually turn to a gas. There's another phase or transition when a solid goes to a gas. That's called sublimation. So these things have a name. A solid going to a liquid is melting. A liquid going to a solid is freezing. A liquid going to a gas is vaporization. A gas going to a liquid is condensation. And a solid going to a gas is called sublimation. Dry ice does that nicely. And a gas going back to a solid is crystallization. So those are the three most common phases of matter. And here you can see their description. Here's a little movie.
When heat is applied to a solid, its temperature and vapor pressure increase with increasing temperature because the molecules of the solid have increasing kinetic energy. At the melting temperature, heat is absorbed as the solid is converted to liquid at a constant temperature. When melting is complete, the temperature of the liquid and its vapor pressure increase. At the boiling point, temperature remains constant as heat is absorbed to convert the liquid to the gas phase. When all the molecules are in the gas phase, the temperature again increases as the gas phase molecules acquire additional kinetic energy.
So what that movie demonstrates is that you can go from one phase to the other phase of matter by applying heat. But notice that you don't cause a chemical change. So again, this is a description of the different phases of matter. The reason why you would have a solid and a liquid is actually because matter sticks to each other. That phenomena is called intermolecular forces. It's what holds one water molecule next to each other. The demonstration that I have here shows one ethanol. This is a structural form of ethanol, and it's connected to another ethanol by something called hydrogen bonding. That's why ethanol molecule sticks. On the other hand, the bonds that connects one carbon to the other in ethanol is called intramolecular force. We are going to see more about that in future lectures. But the reason why we have phases of matter is by a phenomena called intermolecular force. This right here is what we call heating-cooling curve. The curve illustrates to you what happens when you take solid ice at -40 and you start applying heat. As you start applying heat, the solid ice starts to gain temperature, starts to heat up, but it's still in a solid form, it's still in the ice form. Only when you reach 0 degrees does that solid ice starts to melt. So that's called the heats of fusion or the melting process. Here, as you can see from this illustration, you go from solid ice to liquid ice water. And here is an illustration, a pictorial view of liquid water and solid ice in equilibrium, in coexistent. Only when the last solid melts, the last crystal of ice melts, does the temperature goes up again. And it goes up at 1 calorie per, goes up 1 degree for every calorie that's input. So here you see the temperature starts to go up again as you apply more heat, and then when it reaches 100 degrees, the temperature stops rising. And that's because what's happening is you're breaking the water molecules away from each other. You're forcing them to separate, and you're breaking the intermolecular forces between them. So that's the reason why the temperature stays constant, because the water molecules aren't moving any faster. They're just breaking apart. So here what we have is a liquid gas mixture, and so what you have is boiling water right here. Only when the last liquid drop of water is evaporated does the gas or the steam starts to rise in temperature. So the movie that I want to show you is how at the molecular level ice actually melts, and what you want to see is how ice is sort of attracted to each other, but as you apply heat they start to maneuver, or they start to get dislodged from each other. So take a look at this. There's no voice on this. It's just an illustration. So what you see here is when water is solid ice, they actually form these tubes. And that's why when you take liquid water and you freeze it, it actually expands, because they have to have these organization in which there's huge volume in between. And then as you heat it up, notice how the water molecules are sort of vibrating. As you apply more heat, it vibrates even more until they break apart from each other. And look at the edges, because that's where the water starts to melt, and then the water molecule starts to loosen up, and then they are going to mingle among each other. It's not organized anymore. But that's the melting process. When you take solid ice and you start applying heat and it starts to melt, gets to the point where the volume is going to be more compact. That's why liquid water has a smaller volume than solid ice for the same amount of mass. That's why liquid water has a greater density than solid ice. So let's move on and let's take a look at the way we classify matter. Matter can be separated either as a pure substance, which is a mixture of, which is one or two atoms that are bonded together, or a mixture, which is a combination of pure substances. If you take a look at pure substances, it can either be classified as elements like oxygen, carbon, sodium, lead, gold. Those are examples of elements, or compounds. Carbon dioxide, the gas that you breathe out. Water, sodium chloride, sodium cyanide, ether, alcohol, ethanol, that is. The alcohol that you drink is actually a mixture of water and ethanol. And then if you look at mixtures, you could either have a heterogeneous mixture, which is a mixture that is not homogeneous, that has inconsistency. Like if you take a little bit of sand and water, that's a heterogeneous mixture, because the sand doesn't dissolve in the water and you can see two layers there. Or vinegar and oil, or as the example shows, garbage. Homogeneous mixture, however, are a mixture that is consistent throughout. Like if you take salt water and you don't put enough salt, but you can taste the salt in the water, it looks like pure water, or your alcoholic beverage, or gasoline. So compounds are single substances with two or more different elements, and here are some examples: sodium chloride, sugar, baking soda, water. And elements are substances with one type of atom in it, and that could be iodine, as you can see right here. Diamond's actually a form of carbon. Graphite's another form of carbon. And mercury, which is a pure element. Then we have homogeneous mixture. Gold, if it's 24 karat gold, it's pure gold. If your boyfriend gave you a 12 karat gold jewelry, then return it, because that's only half gold. 14 carats, about 60% gold. 22 karat is actually pretty good gold value. And the reason why they make gold an alloy is because gold in itself is very soft. So if you have a jewelry made out of pure gold, it'll bend and warp on you. By putting a different metal in it, it makes it harder. Wine is actually homogeneous. It's got alcohol, water, and some other chemicals in it. And Whipped cream is actually a homogeneous mixture of gas and some sort of solid. Heterogeneous mixtures, examples of that are like sand or some sort of granite, or emerald or some sort of mineral, or tossed salad or salad dressing. These are all inconsistent mixture.
In this experiment, we will first make a mixture of black iron filings and yellow sulfur powder. Black iron filings and yellow sulfur powder are thoroughly mixed. They form a gray mixture of the two elements. This mixture can be separated by physical methods. For example, when a magnet is brought to the mixture, it removes essentially all the iron filings, leaving the sulfur behind, which here looks gray because of the impurities from the iron. The iron has been separated from the sulfur by means of a magnet. When the same mixture is heated in a test tube, the two elements iron and sulfur react together to form a new compound, iron sulfide. At first, when the mixture is heated, the sulfur melts. Eventually, as the heating continues, the iron and sulfur begin to react together. When the Bunsen is removed, the tube continues to glow as the reaction proceeds. The gray-black brittle solid formed is a new compound, iron sulfide. It is unlike either sulfur or iron and cannot be separated by a magnet.
So that's an example of how you can take two elements, iron and sulfur, and you can see its physical properties. They're both solid, and when you mix it, how you get some sort of a mixture, heterogeneous mixture really. And then as you cause the two chemicals to combine by heating it up, you form a new compound, and so you have a chemical change that takes place. So other forms of matter are compounds or pure substances, and here are just a few of the pure substances that are pretty lethal. Tear gas is actually a mixture of compounds. It's got these chemicals in it, and it actually attacks your tear duct, and it makes you tear up. But these chemicals smell, and they contain ethyl bromoacetate and chloroacetone. They're colorless to light yellow, and they have a pungent odor, but they give you they irritate your eyes and mouth. Chlorine, you can easily get chlorine poisoning by mixing bleach and some acid, or bleach and ammonia. Please don't do that, because chlorine is the same chemical that was used in World War I in terms of chemical warfare agent. Phosgene and mustard gas are also chemicals. These are pure compounds in which was used in World War I in chemical warfare agents. So here's some description of tear gas. You can see that it's from it's lacrima, meaning tears in Latin. This is sulfur mustard. Sulfur mustard, commonly known as mustard gas, class of related cytotoxin. And this is again the different classifications of matter. The first one, you can see that there's two white atoms and one dark one. This is probably a representation of water. H2, these are two hydrogens, O. Okay, this is probably a representation of an element, a pure element, it could be either helium or xenon or some other element in which there's only a single atom involved, and that's probably a noble gas. This is an example of a mixture. What we have here is probably oxygen, O2, and then or hydrogen. The blue balls are hydrogen, the red balls are oxygen, and what we have is H2O right here. Okay, and this is a another representation of a pure mixture. Well, it's a pure compound, and this might be carbon monoxide, where there's two different elements that are bonded to each other. And this might be a representation of here you have, say, sulfur and two irons, or you can have two carbons and 4 sulfurs. So this is a mixture as well. Now let's take a look at these examples and let's see whether you recognize them as either an element, a pure substance or compound, a mixture, heterogeneous or homogeneous. Ethanol. What do you think ethanol is? Ethanol has a formula C2H5OH. Charcoal. That's what you see at the bottom of your barbecue. Sand. You find that on the beach. Water. Get it from your faucet. And sugar. You probably get it from your kitchen cabinet. Sugar has a formula C12H22O11. Sugar or sucrose is a pure compound. Water is a pure compound as well. Sand is a heterogeneous mixture. It probably has different materials in it, like maybe small minerals as well as maybe small wood granular. Charcoal is carbon, actually carbon, and ethanol is another pure substance. So these are how you determine whether something has a physical change or a chemical change. In a physical change, you're basically changing its form and you're not changing its identity. And in a chemical change, bonds are breaking and new bonds are forming so that the new identity is different from the original. And here are examples of physical change versus chemical change. When you put sugar in water, that's actually just a physical change, because when you evaporate the water, you get the sugar back up. Cutting wood, there's really no chemical reaction involved. Yeah, you're making the wood smaller, but that's still a physical change. Applying glue, that also is a chemical, physical change. You're not really changing the composition of the glue. Melting ice, you guys know about that, and breaking glass. Those are all examples of physical change. Example of chemical changes is when you take sugar. When anything burns, it's actually a chemical change. Wood burning, sugar burning. A synthesis, when you mix two components and get a new one, like nylon synthesis, that's a chemical change. Electrolysis is actually the decomposition of water. And doping glass is when you embed a different atom in the silicon oxide structure of glass, so that it becomes harder and more difficult to break. That's how you make glass, bulletproof glass. So here's an example of how you would make slime, and that's a chemical change. PVA stands for polyvinyl alcohol. interacts to it actually polymerize, and that's a pretty fun experiment to do because the slime is pretty harmless. And we usually do that in lab if we have a lab, and you can actually we do that for like my class before Halloween. We make some slime. When you have matter and it's mixed, you can actually separate them by some sort of experimental technique. This first one right here towards the bottom is distillation. You're exploiting the fact that one form of matter has one form of the mixture has a higher or lower boiling point than the other, and so if you heat it up, the lower boiling point component will evaporate and you can collect it in this cold condenser. This right here is chromatography. It has to do with the fact that the different chemicals are going to go through a solid with different times because they interact with the solid differently. This is recrystallization, the fact that some materials will form a solid at lower temperatures. This is filtration. This is when you can actually collect the solid that forms during recrystallization. Let me just show you a demonstration of chromatography. So this is an experiment that we used to do in one of my labs, and what we would do is just take some water-soluble ink and put it in a piece of paper, and then we put some sort of alcohol water mixture and some salt, and we allow that capillary action of the liquid to go towards the paper, and as it starts interacting with the ink, some of the components will move faster with the liquid versus the other component, and you get the separation. So I'm going to speed this up shortly here, and you can see the different color separations of these water-soluble ink. So here you can see that the green originally over here actually has some blue and yellow component. The red has some orange component right here. This right here is how they test for drugs. What they do is they run a control, and the control would probably be number 4 here. It has heroin, methamphetamine, and cocaine, and then they run the different samples, and if it matches up, they can tell what drug is present. So chromatography is used a lot in forensic chemistry or for forensic investigation. Anyway, you get the idea here in terms of this particular experiment. You can see that the different mixtures for that color are actually separating. So that's a summary of Chapter 1. The first part of Chapter 1, it talks about matter, its classification and its phases, and how we are able to determine whether we have a physical or chemical change for matter.